Today, we're going to do a deep dive into understanding output level controls, which is controlling the privacy of outputs for a complex computation. We'll explain how it's possible to keep strong privacy controls even when you have a very long and complex data processing pipeline. To do this, we'll introduce the notion of privacy units, which is the entity we want to track and make sure their privacy is protected. We'll give a short intro to differential privacy, very short, and we'll study computational graph to finally put all the pieces together and explain how at Sarus we control the security and the privacy of outputs. So our starting point is this table here where we've marked the individual. So if you want to protect privacy or preserve confidentiality of personal information, you need to define what an individual is. It could be that one row is an individual, but it could be something more complex. The entity we want to preserve is called the privacy unit. Anytime we have a data frame, any data holding object where we're able to track the privacy unit or the individuals, we'll mark them as purple, and we'll have this little person silhouette in it. So now we can start like building computations, and so we have this data frame where we know where the individuals are, and we can apply transformations to them. So when we apply transformation, we have this circle here, and the result of it is going to be another data frame. There's one type of transformations that matter a lot. We call them privacy unit preserving, or PUP, mark them as purple as well. They are transformations for which we're able to keep track of where the users are in the output. Simple example, you have a data frame, plenty of columns, you're selecting one column. It's easy to keep track of where the users are if you know where they are in the input. Keep the columns, structure didn't change, they're in the same place in the output. We also have PUP transformations that could be a lot more complicated, like joins or stuff like this, but it's important to know that for some, we're able to track exactly where individuals went. So we'll mark them at PUP. We have this nice property where if you have a data set where you track the privacy unit, and you can track where the users are in the transformation, then you inherit a data set that has the same property, still in purple, and we can still track privacy units. We have other kinds of transformations where that yield an aggregate. So you put all the users, you compute and whatever, count how many you have, or do a mean, or some statistical analysis on them. You no longer keep track of individual users, you aggregate them together into an output. So we'll mark those ones as ag, and they have a orange output. Per se, this is not much of a guarantee. It's just an aggregate. Could be you're aggregating for one user. So it's not a very satisfying definition. We'll have more interest in one particular type of aggregates, those that have a mathematical guarantee that you cannot use this information to revert back to one user. This mathematical definition is called differential privacy. I invite you to look at other resources to get a deeper dive into this. For what matters to us, we'll just mark those transformations as DP and put a lock next to the result. That means that the result is protected in the sense that it's guaranteed that there's no track of one user, of one privacy unit. It's kind of like building, we have our building blocks, we stacking transformations on data frames here. Unfortunately, not all transformations are either preserving the privacy unit structure or differentially private. Most of them are unknown. We'll mark those as unknown. If you apply an unknown transformation to a data set where you were able to track the privacy units, you have no guarantee on the output. You don't know where the users are anymore. Maybe they all mixed together. Maybe you kept just one. You have no clue. Also, they don't have any privacy guarantee. So we'll mark this as gray. We don't know. So what properties do we have? Well, it has this first property that's very useful, which is composition. If you take a data frame with tracking activated, so you can track the privacy units, and you apply a PUP transformation, you still have a data frame with the same property. You can apply a new one, you still have the property, and so on and so forth. It's actually very, very common when you're doing pre-processing in machine learning, or when you're doing processing and SQL analysis, that most of the transformations you make have this property. So you can have a very long computational graph that is just hacking up transformations that don't impact the distribution of users. And then we have this other property, which is if you have PUP or a privacy unit in the input and you apply a DP output, then you have differential privacy in the output. So that's going to be very cool. We can use this to make sure some outputs can be secured. So let's try and see what we can do. The goal here is to look through the building of a complex computation and try to get like the result of every step along the way and see what could be retrieved. So for example, we start with our data set and the data practitioner, the data scientist requests to retrieve this object. Of course, if you want to protect privacy, you're probably not authorizing to output the input data, the actual source data. So this request by Sarus will be blocked. Instead, we'll fall back to responding with synthetic data. It's a bit underwhelming. You'd rather see the real data, of course, but it's blocked. And what's important to us is that it doesn't prevent you from keeping on building on top of it. So for example, you apply a first transformation here, PUP transformation, you have a new data set, and you ask to retrieve this object. And again, it's going to be blocked because you're retrieving an object where users are. So even maybe you deleted the names, was your PUP transformation, but still this information is very easy to link back to individuals. You're not allowed to see this. So if you retrieve this second object, what you get in return is the synthetic data transformed by this transformation. So you take a synthetic data as input, apply this transformation to it, except for removing the names and whatnot, and you get like a synthetic version of the output. Still not what you want to do. You want to get take the insights from the real data, but again, it would be impossible. You're actually technically asking for the data here. So adding a new one, same story goes again. You're asking for retrieving the user information. It's blocked, so you get your series of transformations applied to synthetic data. But here's what happens when at the very end of your SQL pipeline, now you're requesting an aggregate. And that's super important. Like we were able to keep track of users through all those steps. So when you're requesting a DP aggregate, well, this can be computed and sent back to you based on the real data. So that's why when you ask to retrieve this output, you get agreement, it's validated, tick the box, and we can actually now fall back to using the source data, apply those two PUP transforms and then the DP aggregate, which is what you see here. And now the actual results you get is the true results coming from the real data. So in this construct, you can see that you can, every step along the way, you can see what objects you're manipulating behind the software. But of course, until you get to a point where there's a guarantee that it's safe, you'll get synthetic data representation. But at the end of your pipeline, which is mostly where you want to go if you're doing SQL analysis or machine learning, you get a protected result, in this case, a DP result. Unfortunately, like if there's any unknown transformation somewhere in the pipe, then we can't guarantee anything anymore. So even if the next transformations are PUP or DP, it's too late to say anything. So think of this unknown transformation as, well, you can take one user and duplicate them 1 billion times. And now every statistic is going to be just that user's information. So you can't trust anything anymore after there's an unknown transformation. So you see here, in this case, this unknown transformation and circle red prevents you from having guarantees down the line. You no longer know where users are, so you won't be able to keep track of them. And the only way to give you a safe output automatically is to apply this combination of the unknown function and the other PUP or DP transformations applied to the synthetic data, which would be safe, but a bit underwhelming because you're just processing synthetic data all along. So for this, we've added exceptions. Exceptions is not something that we, Sarus, guarantee in any way. We have this notion of a whitelist. It's a list of transformations that the data owner considers safe enough, that they consider the output to be safe enough to be used by a data practitioner so that they can process the data and just retrieve the output of the safe function. Oftentimes, you can build attacks from safe functions. So please, the whitelist, you want to use them with people you trust, not to be building attacks. I'm going to give you an example. It makes sense to consider machine learning model performance of a machine learning model as safe, because if you're just building in a very natural way machine learning model, the performance of it is not going to be a privacy risk. At the same time, it's easy to use performance of models to hide private information if you're like a malicious actor. So it's both very natural to consider performance of machine learning models safe, also risks, and you want to make sure you use this with people you trust. But now we've added this last break, which will unlock a lot of potential. So again, this is marked as a whitelist by the data owner, not by Sarus. We don't have any opinion. We can give you suggestion, but we don't have an opinion on the safety of this. It's about the safety of who uses it and for what. So in this example where we had our unknown operation here, for example, if the last transformation is to output the performance of the model that you've trained with all the previous steps, it's been whitelisted, then that means that you can actually use the real data, apply the transformations, and the final output comes from this whitelisted transformation. It's allowed to be out. So again, you didn't see the input data in the first place. You didn't see the first transformation of the input data because it was not marked as safe. You didn't see the second transformation of the input data. The last one has been validated manually by the data owner, so it's safe to share. So now we have our full list of elementary blocks. So we have these properties. If you start with privacy unit data frame and you apply a PUP transformation, you inherit a privacy unit data frame. If you apply a DP transformation, you have a protected result. If it's unknown, it's unknown. You can get out of it. If you start with unknown, whatever you do, you get unknown in return. If you start with a DP result, whatever you do is DP, which is also a nice property of differential privacy. And finally, if you start with anything, but you have a whitelist on transformations that consume this, then you're good to go and this result will be safe. So this is how at Sarus we'll use this grammar to analyze any computational graph and tell you what version of the output you're allowed to do, whether it's going to be the DP version, the whitelisted version, or as a fallback, the synthetic version or the version of the graph applied to the synthetic data set. So just for the sake of seeing what it looks like, we have here a typical machine learning model where you extract a data set, you select a column, you rename it, you drop the duplicates, you compute the means, and you fill the missing values by the means, and all of those like they're represented here. You see that you can keep track of the privacy unit all along, all the way down to here where you fitting a machine learning model. And in this case, this random forest classifier, for example, we don't have a DP version. We may have a DP version, but in this case, we don't have one. So we don't have a guarantee on the output. So you would kind of be blocked, but luckily the cross-val score has been whitelisted for you. So you could actually request not the model, you're not allowed to see it, but the cross-val score, in which case we can compute the entire graph. If any, you can do every purple data frame, every purple rectangle is an object for which you can do any statistical computation. So you could at any point of the way request to count the statistics on those purple objects because they're all tracing back to the privacy units at the beginning. So you keep full track of them and you can do DP computations on all of them. So remember, every step along the way, you can compute any statistic with DP. The very last step, we lose track of the privacy unit, but it's not a big deal because maybe this model, all we need to do is to check performance and push to production. We may not need to extract it at any point. This is typically what we do at Sarus. This is actually a very simple graph. Things in real life look a lot more like this, and this is also a simple graph that we could fit in one page. So I hope that was clear. If you have more questions, please reach out. You can do a lot of things with automated protections of the output with Sarus, and this is just the beginning. Thank you.